All right, hello everyone and welcome to Walk Through 5. PSET 5 is misspellings, in which we will be making a spell checker. Now spell checkers are extremely important. Has this ever happened to you? You work very, very hard on a paper for a clash, and then still end up getting a very low grade, like a D or a D equals. And all because you are the liverwurst spoiler in the whale wide word. Yes, proofreading your peppers is a matter of the utmost impotence. Now this is a problem that affects manly students. I was once told by my 6th grade torturer that I would never get into a good colleague. And that's all I ever wanted. That's all any kid wants at my age, just to get into a good colleague. And not just any colleague. No, I wanted to go to an ivory legal colleague. So if I did not improvement, gone would be my dreams of going to Harvard, jail, or prison. You know, in prison, New Jersey. So I got myself a spell checker. That's a little excerpt from one of my favorite spoken word artists, Taylor Mali. Anyway, as he says, the importance of having a spell checker is very important. So, welcome to Walk Through 5, in which we will be talking about PSET 5 misspellings, in which we will be making our very own spell checker. The toolbox for this week, the distribution code, is going to be important to look at just to understand the different functions that your dictionary is going to have. We're actually going to be having multiple .c files that together make our PSET. And so looking through the different aspects, even though we're actually not editing one of the files, speller.c, knowing how it works with relation to dictionary.c, which we will be writing, is going to be pretty important. The PSET spec also contains a lot of useful information in terms of things that you can assume, rules and things like that. So be sure to read the PSET spec carefully for tips, and when in doubt of a rule or something like that, then always refer to the PSET spec or discuss. This PSET is going to rely heavily on pointers, so we want to make sure that we understand the difference between adding stars in front of the pointer's name and ampersands, how to free them, etc. So being a master of pointers is going to be very helpful in this problem set. So then we're going to look into linked lists a bit more, where we basically have elements that we call nodes that have both a value as well as a pointer to the next node. And so essentially linking different elements one after the other. And so there are a few different options of implementing your actual dictionary. We're going to look into two main methods, which is hash tables and then tries. And so in both of those, they involve some kind of notion of a linked list, where you have elements linked to one another. And so we're going to look over how you might be able to operate around linked lists, create them, navigate in terms of how to, for instance, insert a node into it or free all of the nodes as well. In terms of freeing nodes, that's really important, that whenever we malloc memory, afterwards we free it. And so we want to make sure that no pointer goes unfreed, that we don't have any memory leaks. And so we're going to introduce a tool called Valgrind that's actually that basically runs your program and checks whether all the memory that you allocated is then freed. So you don't want to, your PSET is only complete when it works and it has full functionality, but also Valgrind tells you that you haven't found any memory leaks. Now finally, for this PSET, I really want to stress, as usual, I am definitely a supporter of using pen and paper for your problem sets, but for this one, I think that pen and paper is going to be especially important when you want to be drawing arrows to things and understanding how things work. So definitely try to use pen and paper to draw things out before you get coding, because it could get a bit messy. Okay, so first let's go into linked lists a bit. Essentially, linked lists consist of nodes, where every node has a value associated with it, as well as a pointer to the next node after it. And so a couple of things important with a linked list is that we need to remember where our first node is. And then once we know where the first node is, that way we can access the node that the first node points to, and then the one after that, and the one after that. And then the last element in your linked list is that node's pointer is always going to point to null. So when a when a node points to null, then you know that you've reached the end of the list, that that node is the last one, that there's nothing after that. So here in this schematic, you see that the arrows are the pointers, and the blue section is where the value is stored, and then the red box with the pointer to it is basically the node's pointer pointing to the next node after it. And so you see here the D node, the neat D node would point to null because it is the last element in the list. So let's look at how we might define a struct for a node. And since we want to have multiple nodes, this is going to become a type def struct, so in which we're going to have several different instances of nodes. And so we define it as a new data type. So here we have a type def struct node. And in this example, we're dealing with integer nodes. So we have an integer named value, and then we have another pointer, and in this case, it's a pointer to a node, right? So we have a struct node star called next. And then we're calling this whole thing node. Make sure that you follow the syntax. Notice that node is actually referenced up above as well as below the curly braces. And then to keep track of where my first node is in this linked list, then I have a node pointer called head, and I malloc space enough for the size of a node. Notice, however, that that head is actually a node pointer as opposed to an actual node itself. So the head actually doesn't contain any value. It only points to whichever the first node in my linked list is. Okay, so to get a better sense of linked lists, because it's very important to keep track of basically making sure that you maintain the chain, I like to think of it as like people in a line kind of holding hands, where each person kind of is holding hands with the next one. You can't see in this drawing, but basically they're pointing to the next person that is in the line, that is in their chain. And so if you want to traverse a linked list where basically these people, imagine all of those people, they have values associated with them and also point to the next person in the line, then if you want to traverse the linked list, for instance, to either edit the values or search for a value or something like that, then you want to have basically a pointer to the specific person. So we're going to have a data type node pointer. And so, for this instance, let's call it cursor. Another common way to name this would be iterator or something like that, because it's iterating over and actually moving which node it's pointing to. So let's have, basically, we have this here will be our cursor. And so then our cursor will first point to the first element in our list. And so what we want to do is we want to, we would basically be continuing the cursor, moving it from side to side. So in this case, we want to move it to the next element in the list. Now, with arrays, what we would do is we would just say, okay, well, array, we increase the index by 1. In this case, what we need to do is actually find which person, basically this current person, is pointing to, and that's going to be the next value. So if cursor is just a node pointer, then what we want to do is we want to get to the value that the cursor is pointing to. We want to get to that node, and then once we're at that node, find where it's pointing to. So to get to the actual node that the cursor is pointing to, usually we indicate it by star cursor, right? So that would give you the actual node that the cursor is pointing to. And then after that, what we want to do is we want to access whatever that node's next value is. So then to do that, to access values inside of the struct, we have the dot operator, so then it would be cursor dot next. But this is a bit messy in terms of having the brackets around the star cursor, and so we replace this whole statement with cursor. This is a dash and then a greater than sign, so making an arrow, cursor, arrow next. And so that will actually get you the node that the cursor points to, that values of next. So instead of having the star and the dot, you're replacing that with an arrow. So be very careful to make sure that you try to use this syntax. Right. So now that we have our cursor, we want to, if we want to access the value, for instance, before we had cursor arrow next, but to access the value at the node that the cursor is pointing to, we just simply say node arrow value. And so from there, it's just, it's of data type whatever we've defined the values in the nodes to be. So if it's an int node, then cursor arrow value is just going to be an integer. And so we can do operations on that, check equalities, assign it different values, etc. And so then what you want to do, if you want to basically move your cursor from to the next person, then you actually change the value of the cursor. And so since cursor is a node pointer, you change the actual pointer address to the address of the next node in your list. So this is just some code where you could iterate, and where I have the comment do something, that's where you're probably going to access the value or do something to do with that specific node. And so here, to start it off, I say that my cursor initially is going to point to the first element in the linked list. And so before up ahead, I defined it as the head of a node. And so as I mentioned before, freeing is really important. You want to make sure that you free every element in the list once you've basically finished with it, when you don't need to reference any of those pointers anymore. You want to make sure that you free anything, all of those pointers. But you want to be very careful here in that you want to avoid any memory leaks. Basically, if you free one person, for instance, prematurely, then all of the pointers that node points to is going to be lost. So going back to the person example, to make it a bit more high stakes, let's have these people, except in this case they are like hovering over a lake with a monster or something like that. So basically we want to make sure that whenever we free, we don't lose and basically let go of any nodes before we've actually freed them. So for instance, if you were to simply call free on this guy here, then he would be freed, but then all of these guys would then be lost, and they would basically like drift off and fall down. And so we want to make sure that instead we want to basically like maintain a link to the rest. So if we have essentially our head pointer, right, that points to the first element in the list. So it's basically kind of like a rope anchoring the first person. So what you might want to do when you free a list is have basically that if you want to free the first element first, then you can have a temporary pointer, for instance, that points to whatever the first element is. So you have your temporary pointer pointing here. So that way we have a hold of the first node. And then since we know that the first node is going to be freed, then we can basically move this rope, this anchor, our head, to actually point to whatever's the first one is pointing to. So this head actually points to the second element now. Now we are allowed to free whatever is stored in temp, and so we can erase that without it basically endangering all of the other nodes in our list. Now another way that you could do this could be just to free, basically every time you just free the last element in the list, right? Because they're guaranteed not to be pointed to anything, so you could just free this one, then free this one, then free this one. That definitely works, but is a bit slower, because by the nature of the linked lists, we can't just immediately jump to the last one. We have to traverse each element in the linked list and check whether that one is pointing to null, check every time, and then once we reach the end, then free that. And so if you were to do this process, you would actually be like checking here, then checking here, freeing it, then going back, checking here, okay, freeing it, checking here, and then freeing it. So that takes a bit more time. Yeah?
Would it be possible to make a linked list that stores an extra pointer to the end as well as to the front?
That would definitely be possible. Basically, you would have to, okay, so it would, to repeat the question, is it possible to have a linked list structure such that you have a pointer pointing to the end of the linked list? I'd say that's possible, and basically every time that you insert something into your linked list, you would have to like update that pointer and things like that. So you would have basically a node star tail, for instance. But when you're implementing this feature, you have to think of basically the trade-offs, like how many times am I going to be iterating over this? How difficult is it going to be to keep track of the tail as well as the head, as well as my iterator, things like that. So does that, yeah, so it's possible. But in terms of design decisions, you just have to weigh the options. Great, so here is basically a skeleton of code that would allow you to free every element in a linked list. So again, since I'm iterating over a linked list, I'm going to want to have some kind of cursor or iterator, for instance. We are iterating until basically the cursor is null and doesn't. You don't want to iterate when your cursor is null, because that means that there isn't anything in the list, right? And so then here I make a temporary node star pointing to basically like what I'm considering as the first on my list, and then I move my cursor ahead one and then free whatever I had in the temporary storage. Okay, so now we come to inserting into linked lists. Okay, so I have, say, 3 nodes in my linked list, and I want to, let's go with the simple case where we basically want to insert another node basically at the end of our linked list. To do that, all we would do is set we would traverse to find where the current end of the linked list is, so whichever node is pointing to null, that's this one, and then say, well, actually, this one isn't going to be the last node, we're actually going to have another one. So we would have this current one point to whatever we're inserting. And so now this red person here becomes the last node in the linked list. And so the characteristic of the last node of the linked list is that it points to null. So then what we would have to do is set this red guy's pointer to null there. Okay, but what if we wanted to insert a node in between the second and third one, for instance? That one isn't quite as simple, because we want to make sure that we don't let go of any node in our linked list. So what we would have to do is basically kind of make sure that we anchor ourselves to each one. So, for instance, say you just said that, so let's call this the second one. If you said, okay, well, the second one now points to this new one, and you just made a pointer there, then that would result in this guy being lost, because there isn't any there isn't any link to him. Now instead, to draw this again, excuse my artistic abilities. So we know that we can't just directly link to the new one, right? We have to make sure that we hold on to the last one. So what we might want to do is, for instance, let's say, have a temporary pointer to the element that's going to be appended on. And so then we have a temporary pointer there. We can then, since we know that this third one is being kept track of, 2 can now link to our new one. And if this new red guy is going to be in between 2 and 3, then what is that guy's pointer going to point to? Temp, yeah. So then this red guy's next value is going to be temp. Great. Okay, so when you're inserting into linked lists, then we saw that it's a little, we could easily just, add something to the end by creating a temporary array, or we could, if we wanted to add something into the middle of our array, then it would take a bit more shuffling around. So if you want to, for instance, have a sorted linked list, then you have to kind of weigh the costs and benefits of that, because if you want to have a sorted array, that means that every time that you insert into it, it's going to take a bit more time. However, if you want to later on, as we'll find, we will want to search through a linked list, then it might be easier if you know that everything's in order. So you might want to kind of weigh the costs and benefits of that. Another way to insert into a linked list is actually to insert into the very beginning of a list. So if we draw our anchor here, this is our head, and then have these people linked to it, and then we have a new node to be inserted into the beginning, then what might we want to do? Well, what would be wrong with just saying, okay, well, I want to link the red to the blue because that's the first one? What would happen here? Yeah, so all of these 3 would get lost. So we don't want to do that. So again, we've learned that we need to basically have some kind of temporary pointer. So if we so let's choose to have a temporary point to this guy, then we can have the blue one point to the temporary, and then the red point to the blue. So basically, the reason why I'm using people here is because we really want to visualize like holding on to people before and making sure that we have a link to them before we let go of another hand or something like that. Okay, so now that we have a sense of linked lists, how we might create a linked list and create the structures for that, consisting of the type definition for a node and then making sure that we have a pointer to the head of that linked list. Once we have that and we know how to traverse through an array, access various elements, we know how to insert and we know how to free them, then we can get into misspellings. So as usual, we have a section of questions that will get you used to operating with linked lists and different structures such as queues and stacks. Then we can move into misspellings. So misspellings has a couple, in the distribution code, a couple of files of importance. Okay, so first we notice that we have this make file here, which we haven't really encountered before. Essentially, if you looked inside the pset5 folder, you'd notice that you have you have a .h file, then you have two .c files. And so what this make file does is basically, before we would just type make and then the program name, and then we would see all of these basically arguments and flags passed into the compiler. Well, basically what the make file does is allows us to compile several files at once and pass in the flags that we want. And so here we just see that we're going to be, there's a header file here. Then we actually have two source files. We have speller.c and dictionary.c. And you are welcome to edit the makefile if you wish. Notice that here, if you type if you just type clean, then what it does is it actually removes anything like that is the core. If you got a segmentation fault, then basically you get a core dump. So you have this file, this ugly little file appear in your directory called core. And so you want to just remove that to make it clean, removes any exe files and .o files. Let's take a look into dictionary.h. So this says that it declares a dictionary's functionality. And so we have a basically maximum length for any word in the dictionary. We say that this is going to be the longest possible word. It's of length 45, so we're not going to have any words that exceed that length. And so here we just have the function prototypes. We don't have the actual implementation because that's what we'll be doing for this pset. But what this does is basically, since we're dealing with larger files here and larger, like basically functionality on a larger scale, it's useful to have a .h file so that someone else reading or using your code can kind of understand what's going on, and maybe they want to implement, for instance, tries, if you did hash tables or vice versa, then they would say, okay, well, my load function, the actual implementation is going to differ, but this prototype won't change. So here we have check, which returns true if a given word is in the dictionary. And then we have load, which basically takes in a dictionary file and then loads it into some data structure. We have size, which when called returns the size of your dictionary, how many words are stored in it. And then unload, which basically frees up all memory that you may have taken up while making your dictionary. Okay, so then let's take a look at dictionary.c. We see that it looks pretty much very similar to dictionary.h, except now it just has all of these to-dos in it. And so that is your job. Eventually you'll be filling out speller.c with all of this code. Now dictionary.c, when run, isn't really going to do anything. So we look towards speller.c to see the actual implementation of the spell checker. So even though you're not going to be editing any of this code, it's important to kind of read, understand, so when is load called, when am I calling check, just to understand, map it out, see how the function works. So we see that, it's checking for the correct usage. Essentially, when someone runs speller, this indicates that it's optional for them to pass in a dictionary file because there's going to be a default dictionary file. And then they have to pass in the text, essentially, to be spell checked. Our usage deals with time, because a part of this pset, which we'll deal with later, is basically not only getting a functioning spell checker working, but actually getting it to be fast. And so, then that's where our usage is going to come in. So here we see the first call to one of our dictionary.c files, which is load. Essentially, load returns true or false, basically true upon success, false upon failure. And so if the dictionary is not loaded properly, then the speller.c will return 1 and quit. But if it does load properly, then it's going to continue. So we continue, we see some file IO here where it's going to be dealing with opening the text file. And so here what this does is basically spell checks every single word in the text. So what speller.c is doing right here is iterating over each of the words in the text file and then checking them in the dictionary. And so down, oops, I lost it. So then what here we have a Boolean misspelled that will basically see if the check returns true or not. So if the word is actually in the dictionary, then check will return true. That means that the word isn't misspelled. So misspelled would be false. And that's why we have the bang there, the negation. So then we keep on going, and then basically it keeps track of how many misspelled words there are in the file, continues on and closes the file. And then here it basically reports how many misspelled words you had. It calculates how much time it took to load the dictionary, how much time it took to check it, how much time it took to calculate the size, which, as we'll go on, should be very small, and then how much time it took to unload the dictionary. Here up above, we see the call to unload here. If we check for size, here, then we see that here's the call to size, where it determines the size of the dictionary. Awesome. So our tasks for this pset is to implement load, which will load the dictionary data structure, whichever you choose, be it a hash table or a trie, with words from the dictionary file. Then you have size, which will return the number of words in the dictionary. And if you implement load in a smart way, then size should be pretty easy. Then you have check, which will basically check if a given word is in the dictionary. So speller.c passes in a string, and then you have to check whether that string is contained within your dictionary. Notice that dictionaries, we generally have standard dictionaries, but in this pset, basically any dictionary passed in, if in any language, basically. So we can't just assume that, for instance, the word "the" is inside. The word like foobar, for instance, could be defined in a certain dictionary that we pass in. And then we have unload, which frees the dictionary from memory. So first, I'd like to go over the hash table method, about how we might implement all of those 4 functions, and then I'll go over the tries method, how we implement those 4 functions, and at the end talk about some general tips when you're making the pset, and also how you might be able to use Valgrind to check for memory leaks. So let's get into the hash table method. Essentially, a hash table consists of a list of buckets. So every value, every word is going to go into one of these buckets. And so a hash table ideally basically evenly distributes all of your basically like elements or all of these values that you're passing in, and then populates them in the bucket such that basically every bucket has about an equal number of values in them. And so the structure for a hash table would basically be we have an array of linked lists. And so what we do is when we pass in a value, we check basically where that value should belong, which bucket it belongs to, and then place it into the linked list associated with that bucket. So here what I have is a hash function, and so for the first bucket, basically it's an int hash table. So for the first bucket, any integers basically below 10 go into the first bucket. Any integers above 10 but below 20 go into the second, and then so on and so forth. So basically, for me, each bucket is kind of representing these numbers. However, say I were to pass in, I don't know, like 50, for instance, it appears as if, the first three basically contain a range of 10 numbers, but I want to allow my hash table to take in any sort of integers, so then I would basically have to filter out all numbers above 30 into the last bucket. And so then that would result in a kind of unbalanced hash table. So to reiterate, a hash table is basically just an array of buckets where every bucket is a linked list. And so to determine where basically every value goes, which bucket it goes into, you're going to want what's called a hash function that basically takes a value and then says, okay, this bucket, this value corresponds to a certain bucket. So up above, in this example, my hash function basically took each value. If it checked whether it was less than 10, if it was, it would put it into the first bucket, checks whether it's less than 20, puts it into the second. If true, checks if it's less than 30, then puts it into the third bucket, and then basically all else just falls to the fourth bucket. So whenever you have a value, your hash function will place that value into the appropriate bucket. And so then the hash function basically needs to know how many buckets you have. So your array, your hash table size, basically the length, the number of buckets that you have, that's going to be a fixed number that is up to you, for you to decide, but it's going to be a fixed number. So your hash function will be relying on that to determine which bucket every key goes into, such that it's evenly distributed. So similar to our implementation of linked lists, now every node in the hash table is actually going to have a type char. And so we have a char array called word, and then another pointer to the next node, which makes sense because it's going to be a linked list. And so remember when we had linked lists, I made a node star called head that basically was pointing to the first node in the hash table. First node in the linked list. But for a hash table, because we have multiple linked lists, what we want our hash table to be like, what is a bucket? Well, a bucket is actually just a list of node pointers. And so every element in the bucket is actually pointing to its corresponding linked list. To go back to the schematic, you see that the buckets themselves are the arrows, not actually the not actual nodes. Okay. So one essential property of hash functions is that they're deterministic. So that means that whenever you hash the number 2, it should always return the same bucket. So every single value that goes into the hash function, if repeated, has to get the same index. And so your hash function returns basically the index of the array where that value belongs. And so, as I mentioned before, the number of buckets is fixed, and so your index that you return has to be less than the number of buckets, but greater than 0. So hash functions, for it to work out, basically, the reason why we have hash functions instead of just one single linked list or one single array is that we want to be able to basically jump to a certain section most easily. If we know the characteristic of a value, instead of having to search through the whole entire dictionary, being able to kind of jump to a certain section of it. So your hash function should take into account that, ideally each bucket has approximately the same number of keys. Now, since the hash table is a series of linked lists, then the linked lists themselves are going to have more than one node. So in the previous example, 2 different numbers, even though they weren't equal, returned when hashed, would return the same index. So when you are dealing with words, one word would be the same when hashed would be the same like hash value as another word. And so that's what we call a collision, when we have a node that when hashed, the linked list at that bucket isn't empty. And so what we would, the technique that we call there is linear probing, where basically you like go into the linked list and then basically find where you want to insert that node because you have a collision. So you can see that there might be a trade-off here, right? So basically if you have a very small hash table, so a very small number of buckets, then you're going to have a lot of collisions. But then if you make a very large hash table, you're probably going to minimize the collisions, but it's going to be a very large data structure. So there's going to be trade-offs with that. So when you're making your pset, try to play around between maybe making a smaller hash table, but then knowing that you're probably going to have, it's going to take a bit longer to traverse the different elements of those linked lists. Okay, so what load is going to do is iterate over every word in the dictionary. It passes in a pointer to the dictionary file. So you're going to take advantage of the file IO functions that you mastered in pset4 and basically iterate over every word in the dictionary. And so you want every word in the dictionary to become a new node. And you're going to place every one of those nodes inside of your dictionary and data structure. So whenever you get a new word, you know that it's going to become a node. So you can go straight away and, for instance, and basically malloc a node pointer for every new word that you have. So here I'm calling my node pointer new node, and then I'm mallocing what? Well, the size of a node. And then to read this actual string from a file, because the dictionary is actually stored by like a word and then a new line, what we can take advantage of is the function fscanf. So whereby file is the dictionary file that we're passed in. So it scans the file for a string and places that string into the last argument. If you recall back to one of the lectures when we went over and kind of peeled the layers back on the CS50 library, we saw an implementation of fscanf there. So to go back to fscanf, we have the file that we're reading from. We're looking for a string in that file, and then we're placing it into, here I have new node arrow word, because new node is a node pointer, not an actual node. So then I'm saying, okay, well, new node, I want to go to the node that it's pointing to and then assign that value to word. And so then we want to then take that word and insert it into the hash table. Realize that we made new node a node pointer because we're going to want to know what the address of that node is when we insert it in, because the structure of the nodes themselves of the struct is that they have a pointer to a new node. So then what's the address of that node going to point to, where it's going to point, that address is going to be new_node. Does that make sense why we're making new node a node star as opposed to a node? Okay. All right, so we have a word that value is new node arrow word. So that contains the word from the dictionary that we want to input. And so what we want to do is we want to call our hash function on that string, because our hash function takes in a string and then returns us an integer, where that integer is the index where hash table at that index represents that bucket. And so we want to take that index and then go to that index of the hash table and then use that linked list to insert the node at new node. And so remember that if, however you decide to insert your node, whether it's in the middle if you want to sort it, or at the beginning or at the end, just make sure that your last node always points to null, because that's the only way that we know that where the last element of our linked list is. Okay, so if size represents an integer if size is an integer that represents the number of words in a dictionary, then one way to do this is that whenever size is called, we go through every element in our hash table and then iterate through every linked list within the hash table and then calculate the length of that, increasing our counter one by one. But every time that size is called, that's going to take a long time because that's essentially, we're going to be linearly probing every single linked list. Instead, it's going to be a lot easier if you keep track basically of how many words are passed in, right? So then if you include a counter within your load function that updates as necessary, then counter, if you set it to a global variable, will be able to be accessed by size. So what size could simply do is just in one line, just return the size, the counter value, the size of the dictionary, which you already dealt with in load. So that's what I meant if you implement load in a helpful way, then size is going to be pretty easy. Okay, so now we get to check now we're dealing with words from the input text file. And so we're going to be checking whether all of those input words are actually in the dictionary or not. Similar to Scramble, we want to allow for case insensitivity. So you want to make sure that all of the words passed in, even though they're mixed case, are going to, when called with string compare, evaluate are equivalent. And so the words in the dictionary text files are actually all lowercase. Another thing is that you can assume that every word passed in, every string, is going to be either alphabetical or contain apostrophes. And apostrophes are actually going to be like valid words in our dictionary. So if you have a word with apostrophe S, that's an actual like legitimate word in your dictionary that's going to be one of the nodes in your hash table. So essentially, check operates with, well, if the word exists, then it's got to be in our hash table, right? So if the word's in the dictionary, then all of the words in the dictionary in the hash table. So let's look for this word in the hash table. Now we know that since we implemented our hash functions such that every word will always be hashed to the same, every unique word is always hashed to the same value, then we know that, well, instead of searching through our whole entire hash table, we can actually find basically the linked list that word should belong to. If it were in the dictionary, then it would be in that bucket. So what we can do, if word is the name of our string passed in, then we can just hash that word and look at the linked list at the value of hash table index hash word. And so from there, what we can do is we have a smaller subset of nodes to search for this word. And so we can traverse the linked list, use an example from earlier in the walkthrough, and then call string compare upon the word and the current wherever the cursor is pointing to, that word, and see whether those compare. Now, depending on the way that you organize your hash function, if it's sorted, then you might be able to return false a bit earlier. But if it's unsorted, then you want to continue traversing through your linked list until you find the last element of the list. And if you still haven't found the element by the time you've reached the end of the linked list, well, then that means that your word doesn't exist in the dictionary, and so that word is invalid, and so check should return false. Okay, so now we come to unload, where we want to free all of the nodes that we have mallocked. So essentially, free all of the nodes inside of our hash table. So we're going to want to iterate over all of the linked lists and free all of the nodes in that. So if you look above in the walkthrough to the example where we free a linked list, then you basically want to repeat that process for every element in the hash table. And I'll go over this towards the end of the walkthrough, but Valgrind is a tool basically where you can see if you have properly unloaded if you've properly freed every node that you've mallocked, or anything else that you've mallocked, any other pointer. Okay, so that's hash tables, where we have a finite number of buckets and a hash function that will take a value and then basically assign that value to a certain bucket. Now we come to tries. And tries kind of look like this, and I'll also draw out an example. Basically, tries, you have a whole array of potential letters. And then whenever you're constructing a word, that letter can be linked to basically for a dictionary, a wide range of possibilities. Some words start with C, but then continue with A, but others continue with O, for example. So basically, a try is a way of visualizing all of the possible combinations of those words. And so a try is going to basically keep track of the sequence of letters that comprise words. Branching off when necessary, when one letter, can be followed by a multiple of words, and then by a multiple of letters, and then at the end indicate basically at each point whether that word is valid or not. Because, for instance, on your way to, if you're spelling the word mat, for instance, M-A isn't, or at least I don't think it's a valid word, but M-A-T is. And so in your try, it would indicate that, okay, well, after M-A-T, that's actually a valid word. So every node in our try is actually going to contain an array of node pointers. And we're going to have specifically 27 of those node pointers, one for every letter in the alphabet, as well as the apostrophe character. And so every element in this array is going to point to every element in that array is itself going to point to another node. And so if that node is null, if there's nothing after that, then we know that there's basically no further letters in that word sequence. But if that node isn't null, then that means that there are more letters in that letter sequence. And then furthermore, every node indicates whether it's the last character of a word or not. So let's go into an example of a try. So let's say okay, so first I have basically room for 27 nodes in this array. If I have the word bar, do I have a room? How's that room? Okay. So if I have the word bar and I want to insert that in, then, well, the first letter is B. So I'm going to, if my try is empty, then I'm going to make, well, B is the second letter of the alphabet, so I'm going to put that at index. I'm going to choose to put this here at this index. So I'm going to have B here. Now, B is going to be a node that points to another array of basically all the possible characters that can follow after the letter B. In this case, I'm dealing with the word bar. So A will go here. Now after A, I have the letter R. So then A now points to its own combination, and then I'm going to put, and then R will be here. And then bar is a complete word, so then I'm going to have R basically point to another node that says that, another node that basically says that that word is valid. And so that node is also going to have an array of nodes, but those might be null, but basically, so it can continue like that. Now, say I have and that will become a bit more clear when we go to a different example, so just bear with me there. Okay, so now say we have the word so now we have bar inside of our dictionary. Now say we have the word Baz. So we start with B, and we already have B as basically like one of the letters that's in our dictionary. That's followed with A. We have A already, but then instead we have Z following. So then our an element in our array is going to be Z, and so then that one is going to point to another valid end of the word. So we see that when we continue through B and then A, there are two different options currently in our dictionary for words that begin with B and A. Now say we wanted to insert the word foobar, then we would go make a new we would make an entry at F. F is a node that points to a whole array that we would find O, go to O again, and then O, then links to a whole list. We would have B, and then continue. We'd have A, and then R. So then foobar traverses these all the way down until foobar is a correct word. And so then this would be a valid word. Now say we wanted our next word to, in the dictionary is like actually the word foo. Well, we would say, okay, so F, what follows F? Well, I actually already have a space for O, so I'm going to continue. I don't need to make a new one. Continue O. Well, O is a valid, FOO is a valid word in this dictionary. So then I'm going to indicate that that like is valid, right? So if I stop my process, my sequence at there, that would be correct. But if we, like, for instance, continued our sequence from FOO down to B, and so just had FOOB, then foob isn't a word, that's not indicated as a valid one. Okay, so knowing that in a trie, basically you have every node indicating whether it's like a valid word or not, and then every node also has an array of 27 node pointers that then point to nodes themselves. So here's a way of how you might want to define this. However, just like in the hash table example where we had a node star head to indicate the beginning of our linked list, we're also going to want basically some way of knowing where the beginning of our tree is, or beginning of our trie is. Some people call tries trees, and so then that's where like root comes from. So we want the root of our tree to make sure that we stay grounded to wherever our trie is. Okay, so we already kind of went over some, like the way you could think about loading each word into the dictionary. So essentially for every word, you're going to want to iterate through your trie, and knowing that every element in like the children, or we called it children in this case, corresponds to a different letter, you're going to want to check those values at that particular index that corresponds to the letter. So thinking back all the way back to Caesar and Vigenère, like knowing that like basically every letter you can kind of map it back to an alphabetical index. So definitely A through Z is going to be pretty easy to map to an alphabetical letter, but unfortunately apostrophes are also an accepted character in words. And so those, like, I'm not even sure what the ASCII value is, so it's so for that, you know, if you want to find an index, either decide whether you want it to be like either like the first one or the last one. Basically, you'll have to like make a hard-coded check for that, and then put that, you know, in index 26, for instance. Okay, so then you are checking the value at like children I, where I corresponds to whatever letter you're at. And so if that's null, that means that there isn't currently any like possible letters stemming from that previous sequence. So you're going to want to malloc and like make a new node and have that like children I point to it, so that you basically create, when we like inserted a letter into the rectangle, making children non-null and point into that new node. But if that isn't null, like in our instance of like foobar when we already had in our instance of foo when we already had foobar, we continue, and actually we aren't ever making a new node, but rather just setting is word to true at the end of that word. Okay, so then as before, because here basically you're dealing with every letter at a time, it's going to be easier for you for size, instead of having to like calculate and go through the whole tree and calculate how many children do I have, and then like branching off, remembering how many is on the left side and the right side, things like that. It's going to be a lot easier for you if you just keep track of how many words you're adding in when you're dealing with load. And so then that way size can just return a global variable of size. Okay, so now we come to check. Same standards as before, where we want to allow for case and sensitivity. As well, we assume that the strings are only alphabetical characters or the apostrophes, because children is an array of 27 long, so all of the letters of the alphabet plus the apostrophe. So for check, what you'll want to do is you'll want to basically start at the root, because the root will point to an array that contains basically all of the possible like starting letters of a word. So you're going to start there. And then you're going to go to, like, based on, you're basically going to check, okay, well, is this value null or not? Because if the value is null, then that means that the dictionary doesn't have any values that start with that, or that contain that letter in that particular order. So then if it's null, then that means that the word is misspelled right away. But if it's not null, then you can continue, say, okay, well, that first letter is a possible first letter in a word. So now I want to check if the second letter, that sequence, is within my dictionary. So you're going to go to the index of the children of the first node, and check whether that second letter exists. And so then you basically repeat that process to basically check whether that sequence is valid or not within your try. So whenever whenever the node points to the node's children at that index points to null, then you know that that word doesn't exist, that sequence doesn't exist. But then if you reach, for instance, like the end of the word that you've inputted, then you want to check, okay, well, now that I've completed the sequence and found it within my try, well, is that word valid or not? And so then you want to check that, and that's when you, like, basically if you've found that sequence, then you want to check whether that word is valid or not. Because remember back in the previous case that I drew where we had like foob, that was like a valid sequence that we found, but wasn't an actual valid word itself. Similarly, for unload in the tries, you want to unload all of the nodes in your try. Sorry, similar to the hash tables where we, when in unload we freed all the nodes. In the tries, we want to also free all of the nodes. So then unload will actually work easiest from bottom to top, because remember when we're dealing with, because these are essentially linked lists, right? So we want to make sure that we hold on to all of the values and free all of them explicitly. So what you're going to want to do if you're working with a tree is to travel to the bottom and basically free the lowest possible node first, and then go up to all of those children, and then free all of those, go up, and then free, etc. So kind of like dealing with the bottom layer of the the try first and then going up top once you've freed everything. And so this is a good example of where a recursive function might come in handy. So basically, once you've like freed your try, then you like freed the bottom layer, then you call unload on like the rest of it. So making sure that you free every kind of like mini. You can kind of visualize it as like mini tries. So you have your root here, and then that, for instance, like let's say that, I'm just simplifying it so I don't have to draw like 26 of them. So you have these, and then these are basically represent sequences of words where all of these little circles are letters that are like valid sequences of letters. So let's continue just a bit more. Right, so what you're going to want to do is free the bottom here, and then free this one, and then free this one at the bottom before you free the top one up here. Because if you say free something in the second level here, then you actually would lose this value here. So that's why it's important in unload for a try to make sure that you go kind of like free the bottom first. So what you might want to do is basically say, okay, well, for every node, I want to unload all of the children. Cool. So now that we've gone over unload for the hash table method as well as the try method, we're going to want to look at Valgrind. So basically Valgrind, you run it with the following commands. You have Valgrind, flag V, you're checking for all leaks. When you run Speller, given this certain text, because Speller needs to take in a text file. So Valgrind will run your program, tell you how many bytes you allocated, how many bytes you freed. And so it'll tell you whether you freed just enough or whether you didn't free enough, or sometimes you can even overfree, like free a node that's already been freed, and so it'll return you errors. So if you use Valgrind, then it'll output, it'll give you some messages indicating whether you've freed either less than enough, just enough, or more than enough times. And then a part of this p-set, it's optional to challenge the big board, but essentially when we're dealing with these data structures, it's kind of fun to see how quickly and how efficient your data structures could be. So, does your hash function result in a lot of collisions, or is your data size really big? Does it take a lot of time to traverse? So basically, in the log of Speller, it outputs how much time you use to load, to check, to conduct size, and to unload. And so those are posted in the big board, where you can compete against your classmates and some staff members to see who has the fastest spell checker. One thing that I'd like to note, actually, about the hash tables is that there are some pretty simple hash functions that we could think of. For instance, like basically you have 26 buckets, and so every bucket corresponds to the first letter in a word, right? But that's going to result in a pretty unbalanced hash table, because there are a lot less words that start with X than start with M, for instance. And so, one way to go about Speller is, if you want to get all of the other functionality down, then just use a simple hash function to be able to get your code running, and then go back and alter the size of your hash table and the definition. There are a lot of resources on the internet actually for hash functions, and so for this PSET, you are allowed to research hash functions on the internet for some hints and inspiration, as long as you make sure to cite where you got it from. So you're welcome to look and interpret some hash function that you find on the internet. Right. So back to that, you might be able to see, if someone used a try, whether their implementation is faster than your hash table or not. You can submit to the big board multiple times, and it'll record your most recent entry. So maybe you change your hash function and then realize that it's actually a lot faster or a lot slower than before. So that's a bit of a fun way. And there's always one or two staff members who try to actually make like the slowest possible dictionary. So that's always fun to look at. Right. So the usage for the PSET is you run Speller with an optional dictionary, and then a mandatory text file. And so by default, when you run Speller with just a text file and don't specify a dictionary, it's going to use the dictionary text file stored at the large one in the CS50 PSET5 dictionaries folder. And so that one has, I think, over 100,000 words. They also have a small dictionary which has considerably less words stored that CS50 has made for you. However, you can very easily just make your own dictionary if you just want to be working in small examples. For instance, if you want to use GDB and you know the specific values that you want your hash table to map out to, for instance. So you can just make your own text file, for instance, just with bar, baz, foo, and foobar. Make that in a text file, separate those each with one line, and then make your own text file that literally only contains maybe 1 or 2 words, so that you know exactly what the output should be. Some of the sample text files that the big board will, when you run challenge, some of the text files that'll check is like War and Peace and like a Jane Austen novel or something like that. So when you're starting out, a lot easier to make your own text files and that contain only a couple of words or maybe 10, so that you can predict what the outcome should be. And then check it against that, so more of a controlled example. And so since we're dealing with predicting and drawing things around, again, I want to encourage you to use pen and paper, because it's really going to help you with this one, drawing the arrows, where, how the hash table, how your try looks. When you're freeing something, where the arrows are going, are you holding on to enough, do you see any links disappearing and falling to the abyss of leaked memory? So please try to draw things out even before you get to writing code down. Draw things out so that you understand how things are going to work, because then I guarantee you'll run into less pointer muddles there. All right. So I want to wish you the very best of luck with this PSET. I know it's probably it's probably the hardest one. So try to start early. Draw things out, and good luck. This was Walkthrough 5.